Hi everyone, so let's get into section two. We'll be looking at data summary and visualization, and we have four sections, four subsections. Single year map, the year-to-year difference map, the trend analysis mapping, and the time series chart. So these are the four results that we should be getting today. And what we're doing is a series of examples for how to display and explore the first day of the year of no snow that we had just found. And that's basically the data set we had generated in the previous section. And we had just focused on identifying the data and creating an image collection we can work with. So what we're seeing here, these examples, they refer to the calendar date, CalDOI. If you remember what I had talked about in the last video, um, we're talking about CalDOI when displaying and incorporating date information calculations. If you're going to use a date range that begins on any day other than January 1st, let's say July 1st, like I mentioned, then you're going to want to replace RelDOI instead of CalDOI because CalDOI, as I mentioned, is useful when you care about the specific day within the calendar year. Um, so for seasonal analysis, phenology tracking, or anything that's required within a single year, because the calendar year is going to go from January 1st and do the 365 days. That's how it counts the days. When you do relative DOI and you start from July 1st, that's your first day. So it's like it's just it depends, it's user based. So it's helpful when you want to track the number of days relative to a custom start date, which can span multiple years. So let's go check in our new code. So basically what we're going to do is go in the book's repository and go in A2.6b checkpoint. And then this is what you're looking for because we just did the part before and we're looking for what's below for section two. So very short, but it's going to produce a lot of interesting things that are going to be important to us. Okay, and then just go and copy paste in your own code. So when you look at section two, the first thing we're going to do is define a year to visualize. Because the first part is really going to be creating this single year map. But before there are things to consider when you're working the Earth engine, the results are going to appear different as you zoom. If you look at the documentation, due to tile aggregation, um, it might affect the results. So if you zoom in and out of the map, as we'll do, you'll see how it might change how the results appear. So usually it's best to view the map data interactively with a high zoom, and any analysis where a function is going to provide a scale parameter, it's usually best to use the native resolution of the data set, which in this case is 500 meters. And we can double check that, but yeah, it's 500 meters. This is just important because if you're, for example, for region reduction or exporting results, then you want to provide the scale that's going to work best for the image so that your results are as nicely depicted as possible and just as accurate as possible. So another thing to mention too is that with Modis cloud masking, the results may vary, especially locally. If there's many images that are masked image pixel observations, like with clouds or poor quality, then the actual data of the first observation might be affected by those masked image pixel observations. And so the day that is identified for 0% snow cover might actually be earlier than identified in the image time series. Because perhaps when that image, when the first image when there was snow cover was at an earlier date, it could be that it was too cloudy or it was poor quality, so it wasn't considered. So let's say you have a day locally that's like, okay, 0% snow cover, then because of these influences, that date might actually not be super accurate. So it's just important to consider, especially locally. Usually regionally, it'll be less influenced by this bias. So for local results, it's really important to inspect the image masks to really understand what their influence might be on the dates near snowmelt timing. So just important to consider that in your results, they might differ on what available imagery there is, especially depending on what masks you have. And we did add masks for the analysis. but it doesn't take away that you can be using imagery with cloud cover, poor quality, and it's just going to affect your results. So with that said, we're going to start here with the single year map. Okay, so let's get started in the code. So first off, we're going to define the year to visualize because we're going to filter a single year from the collection, 2018 in this case, and display the image to the map to see the spatial patterns of the snow melt timing. So here we've set the minimum and the maximum to a narrow range, just so we can have a good color stretch. And the subset the year of interest, so we're just calling that year that we just called, and then we're displaying it. So let's run the first map and see what it gives us. So what should appear in this layer, because it might take a while, is basically this image here. So this map represents the first day of the year with 0% snow cover. And we're seeing color grades from blue to yellow as the day of the year increases. So when you originally run it, it's going to show you in Oslo. But here we're just going to look at it in North America because in Oslo there's just missing a bit of colors. But you basically have, you can look everywhere on the map. And the thing is, that's why it's so important to zoom in, is because the results, you're going to have different results as you do that. So there's a lot happening here. I'll see if, yeah, so the color that we're seeing that represents the DOI is when it was first observed per pixel, hence why you have a color gradient happening. When you think about the frozen lakes, let's say like Baffin Island, Victoria Island, Banks Island, kind of around this part here, if we look up here, frozen lakes have been shown to decrease air temperatures in pixels, an adjacent pixel, which will result in delayed snowmelt. And then if you look, for example, at the protected estuaries of the Northwest Passages, they have earlier dates than, for example, the areas and the landscapes that are exposed to currents and winds of the Northern Atlantic. So just, if you compare this color gradient to this color gradient, you can see that latitude, elevation, and proximity to ocean currents are some of the strongest determinants in this region when it comes to what region is going to have earlier snowmelt and what region is going to have later snowmelt. And so, as you could have guessed, this gradient is from blue to yellow. It's just showing the timing of snowmelts and blue being earlier and yellow being later. And so you can really see that geographically, her region is going to depend based on what the pixels are adjacent to or close to, and that again is going to give a better idea of the landscapes and the snowmelt you can expect. And then one last thing to note is you can see there's a lot of white happening here. And that's just because the masks are not perfect and that pixels representing glaciers didn't get removed by the analysis mask and they can produce anomalies in the data. And so this is evident, as you can see, when you're looking at the alpine areas of Baffin Island with the glaciers here that are snow covered. So just try to focus on the gradient of color and trying to understand the patterns like we just talked about, looking at what you can see and how that snowmelt is changing. But I mean, in some ways, you can understand the patterns because we're going from earlier to later snowmelt, and here there's in fact snow. So this is going to be an anomaly because obviously there is snow and we're trying to show snowmelt, but you can still understand that from the blue to yellow, there is some form of factor happening and some variables in the making when it comes to what's going to get earlier snowmelt and what's going to get later snowmelt. So that's the main takeaway from this first one. So then we're going to keep going to the rest of the code, and this time we're going to do section 2.2, which is the year-to-year difference map, not just a year. So in this case, we're going to compare year-to-year difference in snowmelt timing, and we're going to select 2 years. So we're going to do between 2005 to 2015, so a 10-year. And by doing so, we're going to do the difference. So quite literally, just subtracting 2015 from 2005 to see that 10-year term and in snowmelt timing. So again, we're calculating the difference. We have the first image with the year, second image with the year, and then we're doing the subtraction, and then we're putting our visualization parameters with still a narrow range for minimum maximum. And then we display it. So it already ran, so I'm just going to show it here. We've got our 2015-2005 map. So what should we expect in this map? It's kind of good to go back to these and just see. So we should be seeing these. So let's see what we can find. So in this case, we're going to be looking at the Himalayas. So let's just zoom in here. Make sure we have about the same area. So it's up to you where you want to go with this. I'm going to keep it at this zoom, but just try to look around the map. And here we're just looking at the Himalayas. So this color represents the difference in each pixel between the 2005 and 2015 day of the year when the 0% snow cover was first observed. So first we're looking at 2018, that 0% snow cover per pixel. Now we're looking at the color in terms of the difference in each pixel. And so red, in this case, represents a negative change and an earlier no snow date in 2015. And blue is going to represent a positive change, which is also a later no snow date in 2015. White, as you can see there's a lot, is a negligible or no change in the no snow dates for 2005 and 2015. And all of that information is found in the description of the image as well. And so this is just to give an example of the positive change and the negative change, because the difference gives you a different perspective of what's happening. And this is just the Himalayas on the Nepal-China border. And if you zoom out, which we'll try to do, you can see that it's not just subject to that location particularly. And obviously we're looking at it a big perspective right now, which is not great in terms of results because you can see the difference of what we're just looking at. But if you zoom in into different areas, you can really look at the negative change and the positive change based on the color gradient and look at when there was an earlier no snow date in 2015 compared to a later no snow date in 2015, like the blue. Um, and then you can see there's quite a lot of white in some areas where there's just no change or negligible at least. So then we're going to go in the third part of the code, which we are here. And in this case, we're going to do some trend analysis mapping because it's also possible to identify trends in the shifting day of the year with no snow. And we do that by calculating the slope through a pixel's time series points. Here, the slope for each pixel is going to be calculated with year as the x variable. And the first day of the year with no snow is going to be our y variable. So this is what's happening here. We're just calculating the slope, and then we're visualizing our parameters and displaying it on the map. So here we're literally looking at it from the whole range of the years from 2000 to 2019. What kind of image are we supposed to look like? So again, here we're working with, I just want to make sure I have the right layer on. Okay. It's going to take a bit of time, but what you can see from this image is you have, again, red, blue, and white. And that means the same thing as the last one, but we're talking about different things this time. So red again is negative. As earlier was a negative change. In this case, it's a negative slope, and it's the progressively earlier first day of the year with no snow. White, again, slope of 0, negligible change, close to none. And then blue is going to be positive, like the positive change is going to be a positive slope. And now we're talking about progressively later first day of the year with no snow. So in southern Norway and Sweden, let's see, the trend in the first day of the year with no snow between 2002 and 2019 seems to be influenced by a lot of factors, like the coastal areas, for example, especially here. You can see that there's a lot more progressively earlier first day of the year of no snow than the inland areas where you can see the blue, which in this case would mean progressively later first day of the year with no snow. But then after that, if you look, for example, in more of the fjords, there's quite high variability in the slopes that can be observed around the fjords and in mountainous regions. You can see like there's a lot of red, but there's blue, there's some negligible change. So it definitely goes, although there's a lot more in the coast areas, you can see that there's a lot of variable change here. This just reveals that there's a lot of complexity in terms of seasonal snow dynamics in these areas, and that in the calculations, the authors didn't do any goodness of fit. That wasn't measured, so there isn't significance considered. And from looking at this, we're looking at slopes, so that can give us an idea of regional trends, especially since we're looking at it from 2000 to 2019. But let's see, if we use the inspector tool. This is just a way to visualize your data, but as you can see, let's say you're new to it and you're like, what does red mean? What does blue mean? Um, you can use the inspector tool and then just see what kind of data it gives you. For example, here we have a positive when we do blue, when we do orange, looking at negative as well, because it's still kind of a gradual. So, but as you can see, there's a lot of variability. There's a lot going on. It's not fully red, fully blue. And so while a slope can indicate some regional trends, more local trends should be investigated using time series charts. So we're going to do that in the next section. This is the last part, 2.4. Again, consider that interannual variability, especially sort of looking on such a big range, will be influenced by mass pixels, as we had talked about earlier with the glaciers. So then let's move on to our last part here. So to understand the temporal patterns of the first day of the year with no snow through time and look at it visually, we can look at it through a time series chart. And in this case here, the authors have created a buffer with a radius of 500 meters around a point of interest, this point here. And then they've calculated the annual mean first day of the year with no snow for pixels within that circle, which is what's happening here. So as you can see, they're basically building the annual mean with producer mean based on this point here. And then you're printing the chart to the console, and this is just the basic chart printing for a time series chart. So let's see what it gives us. It's already been, what's our point? It's let's see what our point gives us. So we're gonna open the chart and see. Okay, so this is the chart for the regional mean first day of year with no snow cover within our region of interest. So let's see where the area of interest is first so we can take a look at what we're looking at. So we're looking at a location in Nunavut. And this is the regional mean first day of year with no snow cover. So in the results, you can see that the first day of the year with no snow was mostly stable from, let's say, 2000 to 2012. But then there's a clear kind of erratic pattern that pops up. And this could have to do with the Earth's warming surface and the expected negative consequences that come with regards to snow cover. You can see a decline in 2014 and then a spike, and it's kind of become erratic. And if you were to calculate it for the next, again, let's say 10 years, it would be important to look at how the regional mean first day of year with no snow cover changes. And this is kind of when we talked about snow timing and seasonal tracking and interannual variability. These are all things that help you consider what's going to happen with snow melt, especially in specific regions. We just looked at Norway and Sweden. We've looked at a little area of interest in Nunavut. We've looked at areas around Baffin Island and the Northwestern Passages, and we've looked at the Himalayas, which are just different examples of how many times you can look at the same data, but in different ways and in different areas, and how it's not just one track thing. And again, we didn't look for accuracy necessarily. We didn't look for good fit. We didn't look for significance. And these are all things that you can add it. So hopefully this gives you just a general understanding and perspectives on snowmelt timing and tracking. So we're going to conclude. To conclude, you should have learned many different things, but mostly how to identify the annual per pixel first day of year with no snow using the MODIS snow cover data. And then you should know how to somewhat analyze snowmelt patterns, and those results can be used to investigate spatial and temporal patterns of seasonal snowmelt. And if we remember the methodology, we added a date band to each image, did some temporal sorting of the image collection, and did an image collection reduction. And when we were reducing mean, for example. Um, and there's a few analyses techniques that we've done, like map and chart, how to interpret those, image differencing, and linear regression. So just different analysis methods that you should have seen already in chapter 1 to 4, but in this case, we're really talking just about application and how you learn all these basic methods and then apply them in things that end up being really important in terms of climate change and livelihoods. So thank you.